Sell you on the idea of reading the manual, because this is where it's not incredibly intuitive how to find this save layer configuration. See how I clicked at the material name on top? That's the only place this comes up. And the only place that it's described really well is in the manual. You've seen it and you're going to say, oh, I'll remember that, but you're going to forget it. Because I always forget it. But it is in the manual. So once you hit click inside here, oh, no, I probably clicked too many times, and it's a left click, you then get a chance to save a new configuration. What's funny is that came up on my other screen. I'm going to have to drag it in so you can see it. Oh, you can see it. Okay. Yeah, and you can still see it. Okay. And then you can give it a new configuration. And I'll just call this one other. To overwrite another configuration, you just click in this box and then select the configuration you want to overwrite. But I'll do the new one. And like I said, I'll do other con. Let's do that. And then you hit save. And then it will be available. So now it's available for you to load. And what I'll do is I'll actually, and you can see here, it's one of the selections. And I'm going to reselect the acoustic. And there you go. As soon as you selected it, you select it like if you had 7 layers in that, you'd get all 7 back. If you had 3, you'd get 3 back. And it will change the layers for you. Change the layers. Up in the top section here, so we covered refractive index. You seem to understand you need that to get the right material thickness. You can put any names you want and type them in as you need. There is a section here for total material thickness. This is where it adds one layer to the next until you get the total thickness. But this first column is the one that I typically am more interested in, right? Because I want to know what is the individual layer thickness of column of layer 4, and this is the column you go for that, right? So it's 0.399. All the 1 through 4 is 3.034 total thickness, but column layer 4 in this column is just 0.399398. And what you can't see, well, I guess you can kind of see it. It's not in the bottom blown up screen, but in the top screen there's optical thickness. Now, so I'm going to say something you can forget about. You know, if you never remember this, it's fine. This is actually what the machine measures accurately, optical thickness, right? Everything else is a conversion, but that's why we display this as optical thickness. All right, so that pretty much covers the measurement data window up top. Let's talk about the waveform quickly. There's a few things going on here, right? There's this green line that slopes up, right? You may wonder what that is. That's actually more for diagnostics. You know the machine is running well if that line is a nice, even line going all the way up. Sometimes it will go and then something's wrong. But that is the way you should always see it. In fact, a lot of customers get so used to it they just turn it off, and you can turn it off if you want to. Then I'll go through the waveform quickly now. I think you understand what's going on. You get a peak at every interface between the glass and the air. That's this peak here. And then you have, this is all glass, your first layer of glass. Then you have another interface where you got glass and plastic, PVB, or PVC, whatever the plastic is. And you get another peak, and that peak is a retroreflection of light going back to the probe, and that's the case every time you see a peak. you're seeing an interface between two different materials. And that's why these numbers indicate you have different materials. Now, just if for some reason your materials had the same index of refraction, you wouldn't see a peak. Just one of the things that we do is we put a little red diamond on top of any peak that's tall enough to be measured. That's why you see these little red diamonds at the top of the blue forms. And that means we've got enough data to calculate a thickness. Pretty much what you need to know about the waveform. Except for one, I'll do one quick thing. You can zoom in on signals. Oops. By holding the shift key down and right clicking and dragging. So if you want to see what that waveform, that first interface looks like in a little more detail, you can zoom in. In fact, you can keep zooming in and make it bigger and bigger. And then you can either auto zoom back out or unzoom. Either way, get you back to where you were. You can control, and I'll talk about the controls, that's next in the settings, but there is one other control you can do in the graphics waveform interface is change the threshold by dragging it up and down. So what I'm going to do is I'm going to take it above the signals in the middle, and you'll see all the other signals went to 0, and now you have the total stack thickness, but it's only calculated with the one index. Because what happens is it doesn't see these peaks anymore, because I brought it above them. See where I put in the Allen key? And that allows you to raise or lower gross height adjustment. Now what I would say, with the 25 millimeter, just go ahead and let it bottom out and tighten it down. And then you'll just do all fine adjustment from there. What happens is there's an ideal location to get these inner peaks, right? So the inner peaks have less light coming back because the index is not as dramatically different. So there's a height where the focus of the probe and the interferometer's sensitivity matches, and it's usually around this area of the scan, and that's what you're trying to find. Where do those inner peaks come up the highest when you adjust the brass ring there? This LED level can go all the way from 0, which is no light, all the way up to, I recommend when you're doing your initial alignment, just start at 128 and see what if you're not at an ideal location, at an ideal height, you can be fooled and it will look like you only have 3 layers, right? So this is the same glass, but it looks like it only has 3 layers. You can see a hint of a hint of a layer here, right? And that's kind of your clue that hey, maybe I should adjust a little more. And that's what you got to do. And by the way, just a little practical thing, since this is a fiber, you don't want to spin this to make a height adjustment. You want to spin on on the glass. And see how when I set the height just right, I get all my 5 layers in. Peak width is interesting. Since you have well-behaved materials, you will probably never change the peak width. 8 is probably fine for everything. So in data processing, you get to do a noise reduction step, which if you, like for example, I'm going to turn mine down to no noise reduction and see how the blue noise came up much higher. And then if I turn it up, I can cause the noise to go down. So what you give up with that is speed. So you're not getting a measurement every 50th of a second. Four basically measurement cycles are used to do some noise reduction. And averaging is similar. You're going to give up speed for accuracy. Sample average is just that. That's how many scans do I average before I present data results. And so if sample average is at 4, your standard deviation is of 4 sample averages. So you can reduce the white noise of your measurements by square root of n sample averages. So you'd get 2 times reduction with 4 sample averages in noise. So that's what standard deviation is. It's actually for the number of scans that are being averaged. Move on there is something you have to keep in mind. We're talking about setting the height, but we actually normally we also are concerned with tip and tilt, right? Now, this probe kind of takes that out of the equation. You don't have to do it because you just do it by dead reckoning, let's call it. There is no tip and tilt here, but in fact there's kind of a hidden tip and tilt. These 3 white balls are what sets how square the probe is to the measurement surface. So if you keep an eye on these 3 white bulbs, make sure they don't start getting flats or dented or worn out, then you know you're in good shape. But if you notice that your signal is starting to degrade and you're not getting the peaks that you used to get, it might be because you're developing wear or flats on the 3 Delrin balls. They're pretty rugged. And glass should not wear them down very quickly. But something like if you set it on a piece of anodized aluminum over and over, eventually you're going to put a flat on those balls. Output type is CSV file, so that can go right into Excel. And it works this way. You pick in folder name, you hit browse, you can pick a place to put it, save it to documents. That's fine, we'll just do that for now. You don't have to give it a name. It automatically names it by date and time, so that you can find it, but you can give it a comment. This is a test, right? And auto name is what I would recommend. You can overwrite or one line overwrite or append, but actually that gets very complicated to me, and that's more for if you have the toolkit in your programming. But just auto naming gives you a new file every time you run a data point. Now you get 3 different ways to decide how much data you're going to get. User input, data points, in other words, I only want 100 scans, or time, I only want 100 seconds. Now user input means it's going to take data until I stop it. And the way you stop and start it is with this red record button up top. So if I click it right now, you can see it says writing file. Yeah, I'm pointing at it, but you know what I'm getting at. You can't see me doing it. But then when you're done, it has now written a new data file to this directory that you called out originally. And that basically covers very quickly the data collection.